Good afternoon, ladies and gentlemen. Welcome to the Ceres Power Holdings PLC investor update. Throughout this recorded presentation, investors will be in listen-only mode. Questions are encouraged. They can be submitted at any time using the Q&A tab situated on the right-hand corner of your screen. Just simply type in your questions at any time and press send. I'd now like to hand over to Director of Corporate Communications, Elizabeth Skerritt. Good afternoon.
Many thanks. Hello, everyone, and thanks for joining us. My name's Elizabeth Skerritt, and I head up Investor Relations for Ceres. Many of you will also have met our Technology Delivery Director, John Hartman, or at the very least seen one of his many publications and podcasts on the topic of hydrogen. Earlier this year, John's team announced a collaboration with Atkins to design a modularised production system for green hydrogen. And today, we are delighted to welcome Gareth Richardson, who heads up low carbon technology at Atkins, to discuss the project in a bit more detail. And then joining them is Chris Leonard, who's the Energy Transition Research Analyst at UBS. He's kindly agreed to host the conversation and try and get to the bottom of where green hydrogen is likely to play a role in the energy transition, which industries will benefit, and how Ceres' technologies can integrate into these solutions. So, as ever, feel free to add your questions via the system's Q&A function. For the purpose of today's session, we are sticking to the topic in hand, but those that are not picked up will be addressed later by the team. So, without further ado, I'd like to hand over to Chris. Thanks, Chris.
Thanks, Elizabeth. So yeah, I'm Chris Leonard from UBS Research on our energy team covering energy transition enablers across Europe. And it's a real pleasure to be invited to moderate the discussion today between Gareth and John. They're both experts in their fields, which means I have the easy job of asking a few questions and steering the discussion, which I'm sure will be educational for all. To kick off the discussion, it would be great to turn to Gareth to introduce himself and the work that Atkins does in green hydrogen. Thanks.
Hi, welcome everyone. Gareth Richardson, the Carbon Technology Lead. I'm the engineering manager on the work we're doing with Ceres, so I've got a good in-depth background on what we're looking at. And in terms of Atkins as a company, it's a global engineering company and project management with 40,000 staff worldwide. We work across pretty much every sector, from infrastructure such as national grid upgrades, major road networks, down to building semiconductor manufacturing plants and mining sites. We even own our own nuclear reactor design, so quite a broad spectrum there as a company. But in the global hydrogen industry, we're actually running one of the US Department of Energy hubs, the Pacific Northwest hub in the US, that's about to receive $1 billion of funding from the US government. And we're expecting that to unlock about $6 billion worth of private investment in that area in the Pacific Northwest. Some of the projects that we work in some of the green space, we're working on green and blue ammonia production, e-methane. So in Quebec, we're part of the design for the e-methane plant there. Green steel, we've done a number of projects there. And in the UK, we're looking at gigawatt-hour salt cavern storage up in the north of England. And we're doing the designs for that, including the designs of the caverns. A lot of these projects are around the UK, North America, the Middle East. And we do a variety of roles in those, from being the owner's engineer on the client side to actually doing the design, all the way through to actually commissioning an ammonia plant, building and commissioning an ammonia plant in Oman last year. In terms of the technology space, we are actually a CTO for a venture capital firm. It's dedicated to aerospace, doing a bit in the hydrogen area there. We're on new technologies in blue hydrogen, and obviously the project we're doing with Ceres to make green hydrogen. So we're really focused on the energy transition and how we can really support that from a technology delivery aspect. There you go, Chris.
Perfect, brilliant introduction across the whole range of the hydrogen delivery systems. That's really helpful. Thank you. And over maybe to John to introduce Ceres' view on the hydrogen industry today and where Ceres is right now.
Yeah, thanks very much, Chris. Hello, everybody. So our technology, so really we started about 5 years ago, 2019, thinking about how we could apply our technology not only for fuel cell applications, but also for producing green hydrogen. And we see a really great fit with the technology in terms of integrating it within industrial processes. So if you can do that, if you can use some fairly low-grade heat from industrial processes to raise steam, then actually you can get some really high efficiency, really low electrical energy consumption for generating hydrogen. So we certainly see our solid oxide technology as a really good fit with integrating industrial processes such as steel production, ammonia, synthetic fuels, synthetic aviation fuel, and e-fuels as well. And that's really what we've been working with Gareth and the team at Atkins to look at how does our technology scale up for industrial applications, and how can we get the best out of it to decarbonize those hard to abate sectors.
So you guys both announced in February this year that you were working together on a modularized electrolyzer system design, and maybe a really good time to just give us a view on how the project is going and what the scope of the work was and is.
Yeah, sure. Shall I take that to start with, and then I'll hand over to Gareth. So we initially we started with a technology demonstrator system, which you may well have seen a fair about on LinkedIn and the press. So we decided in 2021 to build a 1 megawatt class electrolyzer technology demonstrator. We got that up and running last year, and now that is at Shell's Technology Centre in Bangalore, just being commissioned. And that's a really great first start to really understand how our technology is going to work at a system level. But thinking about how the technology is going to scale up and scale out is a much bigger question, really. And for that, we thought Ceres was best partnering with an organisation like Atkins to really think about plant level architecture, really from the outside in. So thinking about integration with electrical systems, downstream hydrogen offtake, and then how do you integrate all the different plant level services together, and what does it mean to scale up the technology into building blocks that can be made at factory level but then deployed 10 megawatt, 100 megawatt, 200 megawatt blocks. So that's really what we started to look at with Gareth and the team earlier this year. I'll hand over to Gareth for a bit more info on that.
Yeah, I think one of the key steps in it was really is bringing those two ends. You understand what the requirements are of the base system, the heart of it, the electrolyzer to stack, and then bringing in, well, what does that end user really need, and trying to bring those two bits together with all that knowledge, so that you actually get a product that the industry wants, rather than forcing your impression of it. You need to understand what the industry wants, and then really drive your design from that, and that's what we've done as part of this project.
And as a follow-on from that, I mean, obviously it's fairly new, a few months into the project, but what have been the key learnings and outputs from this early stage of the study, and how does that align with what the end users are looking for? Maybe Gareth, if you could continue on that.
Yeah, I carry on with that. I guess if we start with what the end user wants, and we can go back to what some of the learnings we've come out of it. I mean, one of the key bits is electrical efficiency. You need to have high electrical efficiency, and SOC allows you to do that. And as John alluded to earlier, when you've got steam available, you're swapping out some of that high value electricity for low value steam. And it still has a cost, but it's much lower cost than it is using electricity. So it allows you to really drive down that the electrical cost of the system. And then when you look at it as a capital cost, that's what the end user want. They want low OPEX, low capital cost, and that's how you get to low cost hydrogen. So what we've really focused on is how do we design the various bits of the plant so that you can scale it vertically. And when I talk about vertical scaling, it's not different to how you make the stack. So a stack you make in multiples, you make lots of them, like cars, right? You're mass manufacturing, and you get down the learning curve on that, and you can get your costs down on that. But if you look at big industrial plants, they haven't gone down that route. They go, right, well, I need to make everything bigger. I need to vertically scale. And a good example of this, if I have a pipe, and a pipe, I make the diameter twice, well, I actually get 4 times the flow, not twice the flow, just by adding the diameter slightly bigger. So it's not like doing sort of horizontal scaling, as I'd call it. You're actually using where you say, need 4 pipes instead of just 1 that's twice the diameter. So you go find those bits of the plant where you can really scale it bigger and get the cost saving from doing that and vertically scaling it, rather than doing the mass production piece. And that's what industrial plants do. They go, right, well, I'm going to make my reactor 0.5 meter bigger and get 4 times the flow or 3 times the flow through it and get the production up. And I got more flow and product to average my capex across. So this is what you're trying to do with this, trying to get that capex down, higher production rate, so that you can average that capex across more production. And that really helps drive down the capital cost by doing that of the plant. So the actual stack of so stack array module, which is what Ceres' core technology is, the stack piece there, that intrinsically, like I said, is mass manufacturable. There's limitations on how big you can make that. But once you take that away, well, what else can I do with that rest of that plant? And you can drive the efficiencies there, I think. And I think that's one of the learnings we've got, is there was a lot of opportunity to do that. And I guess actually coming back to one of the other points about doing that is that where you have electrolyzers that are designed, say 10 megawatt with all their balance of plant and everything, just multiplying those up on a site, developers not a big fan of that when they go and look at that in the market. The feedback we've had from certain developers is that I don't want to go manage 100 10 megawatt electrolyzers with 100 balance of plants. I want to go manage as little equipment as I can, because otherwise I've got 100 pumps, 1,000 valves rather than 100 valves and 100 pumps that I might need. So it's finding out all those different bits from the end user, bringing that into the design to get something that really meets the requirements at industrial scale. So you've got to remember, hydrogen's used in industry now. It's not really used anywhere else. So the scale is big. A steel plant needs hundreds of megawatts of capacity. It's 120,000 ton roughly of hydrogen for, say, 2 million ton steel plant. So that scale really brings to you, well, actually, that's not a big steel plant either. So that gives you the scale that you need to get to. So just multiplying up lots of little electrolyzers with all their balance of plants isn't going to work for that, because your maintenance costs, your operating costs are going to go to the roof. So you really have to find where you're going to get that benefits at that scale and bring that back down to your core design on deciding how big that module is going to be. And we've done that. I think we've got to the right level module, and then we're scaling up the balance of plant now to meet that at the larger scales. So hopefully that gives you a bit of an idea about what we've learned from the project so far.
No, it definitely does, and maybe a good moment to have a look at what the modules look like. And I think we've got a short video to show the output of the work, and maybe John will guide us through that, if we can show that.
Yep, sure. Just a bit of a cover. So this is a bit of a sneak peek of the video. And it's providing an example of a 100 megawatt plant. So we thought it'd be really great to be able to show everyone this today. But as I say, it's the first cut of the video. Hope you enjoy it.
Ceres is a leader in clean energy technology, enabling the world's most progressive companies to decarbonise at the scale and pace needed to achieve net zero. Ceres have leveraged Atkins Realis' global expertise and capabilities in hydrogen across the full value chain to identify opportunities to use Ceres' technology in industrial applications. Together, the two companies will develop an electrolyser module and commercially scalable green hydrogen plant design based on the highly efficient Ceres steel cell electrolyser technology. Let's take a look at how the plant building block is differentiated from low-temperature electrolyser plant designs. At scale, the technology decarbonises industrial sectors, utilising building blocks of 100 megawatts of modules with scaled balance of plant. The plant will produce green hydrogen at a rate of 26 kilotons per annum at 30 bar. Ceres steel cell electrolyser is the latest generation of SOEC technology, which provides the advantage of operating at lower temperatures. This differentiating feature means that Ceres' proprietary technology uses 30% less electricity compared to alkaline electrolysis, when coupled with heat from industries such as fertiliser, chemicals and steel. Not only does this save on renewable power costs, but it also saves significant plant capital costs by reducing the substation size. Ceres' electrolyser module, which, due to the lower operating temperature of the technology compared to other SOEC technologies, removes the need for expensive materials and design complexity. Each 8.6 megawatt DC electrolyser module produces over 6 tonnes per day of hydrogen, with a footprint of only 120 square metres. Designed for optimum performance, the balance of plant is centralised and optimised to recover heat from the hydrogen purification and compression to warm up the feed water, increasing overall energy efficiency and significantly reducing the cooling requirement by 19 megawatts. As the electrolyser module is pressurised, overall performance is improved, and electrical consumption is reduced at plant level versus unpressurised electrolysers. The plant's highest efficiency and lowest capital cost is achieved when integrated with an industrial facility that produces heat, for example ammonia. This allows the plant to replace electricity with thermal energy. Ceres and Atkins Realis' 100 megawatts plant design enables a significant reduction in the cost of hydrogen production, providing the optimum solution for heavy industry transitioning to a cleaner energy future. To learn more, go to ceres.tech.
That's very informative, and I think so some of the key takeaways from that might well also be the obviously the efficiency gain, but equally the footprint that is very impressive. And I just wondered, when you're looking at the key technology asks from your prospective customers across the different industries of ammonia, maybe steel or synthetic fuels, what are sort of the key asks and the key challenges of the current solid oxide electrolyzer technology? Is it that scale up to prove it can go to 100 megawatts and 1 gigawatt upwards? Is it the cost per megawatt? Is it the footprint size, which I've just seen there? Or is it maybe reliability? Like what are the key buckets that you guys need to tick to gain those, the trust and the orders?
Well, I think it's definitely they need to be a reliable supply of low cost energy. That's absolutely key. And it's got to be, like I mentioned earlier, efficient, CapEx, OpEx, and footprint, as you mentioned, is very key as well. A lot of people forget that land costs quite a bit. It's quite often ignored from some of the feasibility studies, but land costs quite a bit. And if you're on a brownfield site as well, so an old steel plant or something like that, where they're trying to build a new site, they can be quite site constrained as well. So having a smaller footprint really, really helps with that. I mean, a lot of industries are looking for 97% availability of the kit they're trying to bring in for hydrogen. They're looking at very high reliabilities in that area, and having a modular system like we have allows us to try and get to that 97%, and that's what we're targeting. The other thing to think about in these areas when you're talking about the industries that we're looking at, the big ones, they don't like going up and down in terms of their throughput. So they really like being steady, which means you need to always have that hydrogen there. So the plant needs to be able to do that. We're either going to have to put large amounts of storage in, like salt caverns, or you're going to have to put a very stable grid connected to it. And again, it also comes down to economics as well with those kind of things. You're trying to achieve at least 65% uptime on everything, because you're just not going to have enough of a product to average your CapEx across. So these projects, they're big and they require a hydrogen plant that can deliver the low cost hydrogen in the right footprint with the right efficiency, the highest efficiency you can get, and trying to really drive down that CapEx to meet that. And some of the areas where you can drive down that CapEx, and it's alluded to in the video, is people forget that the balance of plant is actually quite a large chunk of that cost, and a large footprint as well, which adds to it. And you reduce that with having a higher efficiency by the substation now is much smaller, as I mentioned in the video, but also by cooling is much smaller. I'm not losing as much heat. And one of the real benefits that we probably don't talk about enough when people talk about solid oxide is the fact that it doesn't, over its life, most electrolyzers degrade, and they have to put more power in across its life to keep the same hydrogen production rate. Okay. Now, with a solid oxide, you have an extra handle, an extra variable you can use to adjust that by increasing the temperature in the system, which reduces your resistances and reduces your electrical consumption. So you can maintain the same efficiency by adjusting the temperature of the electrolyzer. So if I'm designing a plant for alkaline or PEM, I need to oversize my substation by 10, 20%. I need to oversize my cooling by 10, 20%. But I don't need to do that with solid oxide. And that is a major benefit in terms of the footprint, the capital cost, and the efficiency. of these systems. So that's why it's a really, SOEC, I think, is a really great tie into industrial facilities where you have that thermal energy that you can replace your electrical energy with.
Yeah, thanks, Gareth. I mean, I think you covered that brilliantly. I think I'll just add what are people looking for as well from solid oxide? Well, they're looking for the availability to buy the electrolyzers as well, right? So and this is something where I think Ceres's particular business model is a real strength. We're a licensing business model, so we license the use of the technology for people to build into products, but we also license the manufacturing, and we've been working with our licensees developing factories for many years, which are scaling up the production of the cells and stacks to many tens of megawatts currently, with plans to go much larger. So actually, the manufacturing readiness of Ceres's technology is there as well. So it's ready to hit the ground really in terms of scaling out the technology, building it into products, and then moving into projects, green hydrogen projects, in a way that we've really brought the experience of our licensees to bear in this regard to really get the technology to a point where it's great quality, high yield, and optimized in terms of its manufacturing cost too. I think there's probably some other points to just embellish on what Gareth said. So one of the key questions is the delivery pressure of the hydrogen as well. It comes up quite often. And typically solid oxide technologies, when they've been working in fuel cell mode, they're operating around atmospheric. They don't need to operate at pressure particularly. And if you just take the technology and run it in reverse and don't pressurize it, it works absolutely fine. But actually, you get a very low pressure out the electrolyzer. And if you're going into an industrial process, that causes some problems, right? So it causes problems in terms of that first stage of compression, because you're going from a very low pressure up to the next stage. That's expensive in terms of energy requirements to compress. It's also expensive in terms of capex. Those low stage compressors are really quite expensive, and they're big, and they take a lot of maintenance actually. So one of the key voices we heard when we were developing our architecture with Gareth was try to deliver the hydrogen at pressure. It doesn't need to be particularly high initially, but even something around 2 bar gets you over that first hurdle to entry, really, those first barriers to entry in terms of getting electrolyzer systems into industrial use.
Yeah, I think the bulk of the energy you need for compression is in the first 2 bar. So you get rid of a huge amount of that, and then the curve after that flattens out. So you as you go up in pressure, there's not as much of an electrical efficiency benefit to doing it. So yeah, it's definitely a big benefit there.
And whilst we're still on the compression angle, how difficult is that to achieve in the electrolyzer design? Getting that 2 bar to become available, is that a challenge which you guys feel like you're still early on the development curve for? Will it be challenging for others in the industry? Obviously, it's still a pretty small nascent electrolyzer or solid oxide electrolyzer industry. Will others struggle to get there? Could this be a differentiator?
I don't think it's necessarily a differentiator. I mean, you've seen in the video those sort of copper-coloured pressure vessels. So we took a decision to actually not ask the stack to withstand the pressure. We're installing the stacks within a pressure vessel, and there's other solid oxide designs which are following a similar approach out there. But I think other companies who may well be set down a certain path in their system designs already and are effectively just reversing those system designs, that's going to be quite a challenge because they're already heavily invested in those factories to build the systems the way they are. So I think it just depends really, but I think we believe that actually having pressurized SOEC for industrial applications has got to be the way to go.
Yeah.
And Gareth, you also spoke about the uptime, so 65% uptime and above, and obviously we need to see utilization being high. Is there anything on this? You spoke about storage, maybe salt cavern storage, and we didn't mention batteries, but clearly grid connection might be important to enable solid uptime. Has there been any other elements of the design that that's needed to be sort of modified to enable solid oxide to stay at high levels of utilization? Or is it responsiveness is actually at a high enough level to be able to move to swings and renewables?
Yeah, so one of part of the requirements piece we captured at the start from Ceres' partners and industry was that it does need to be able to vary with the power source that's coming in. We need to have that ability to do that. So the system's designed to be able to vary with renewable load as it goes up and down, and it can do that in a similar way to the way alkaline electrolyzers do it. So it's able to respond quickly to those and do it. And I guess the point I was trying to make earlier about those kind of things is, yes, you want that, but you don't want to be doing that all day long, because if you're varying your power down low all day long or varying it hugely, well, your production rate's going down. Power equals hydrogen, right? So most big industrial sites, if they want to be economic, have to run at quite high utilizations to actually do it, which means your electrolyzer has to run at high utilizations. Now, you might want to be able to vary it at times to do things, because there's certain things you can do. If you have a bit of storage, you can play some services to the grid in terms of demand response, and you want to be able to do that. So having the ability to have that in the electrolyzer design or accounted for really helps with it in terms of being applicable across the market. I think probably just add one point on what John mentioned earlier about the business model that Ceres has is there's another advantage to that if you think longer term. Having multiple other companies building stacks really helps you with the ongoing maintenance. There's access across the market then. If one company goes down, well, another company will have the production facility there building them. So if you have like a one-stop shop, small electrolyzer company, they don't have that backup there in the longer term. So that's another advantage that we haven't really ever talked about, actually, that Ceres' business model really helps with. It's distributing that risk, that long-term risk in terms of having to change these out. Because don't forget, electrolyzer stacks, like I said, they degrade, so you need to replace them in the life of the plant.
Obviously, we've spoken about how central sort of waste heat will be to improving the power consumption of the solid oxide electrolyzer. And maybe, John, it would be helpful to quickly run through and recap why it is that solid oxide has such a strong hand to play for industrial decarbonisation, and why the technology is quite unique with the high temperature aspect to it.
Yeah, sure. I mean, really, its party trick is operating at high temperature. The stack itself, the core stack. I mean, our operating temperature is between 500 to 600 C. We're lower temperature solid oxide. There are other generations of the technology operate at sort of 750 up to 900. But really, the key efficiency is driven by being able to electrolyze steam. That's really your thermodynamic advantage there. That's where you get the most bang for the buck. So if you can feed steam into the electrolyzer, you're already at the stack level, 34 kilowatt hours per kilogram. At system level, 37, that kind of range. So compared to alkaline and PEM, who are low 50s at best, it's quite a significant gap there. But one of the misconceptions, you need really high grade heat to operate an SOEC system, and that's just not true. As long as you can have steam, 150, 170 degrees C from an industrial process, then that's fine. And actually, what happens in terms of getting the steam up to the temperature required to enter the stack is you have a system of heat exchangers in the electrolyzer module we saw in the video earlier. There's a centralized heat exchanger pack, and that they do the job of increasing that steam temperature to the inlet of the stack. But that's the point. And really, those sort of grades of heat, 150, 170, 200 C, at industrial plant level, they're generally on the way to a cooling tower. There's not much you can do with that grade of heat. It's normally most of the useful work's been taken out of those streams by the time they get to those temperatures. So normally you'd be sending it to a cooling stage or something like that. So actually that's quite a good advantage of solid oxide. You can use those waste streams and you can generate real value from them.
Yeah, I'll probably add there's an important piece on that around the types of industrial technology that we talked about earlier, about fertilizer, about steel, and about e-fuels, you know, if you take fertilizer, it's an exothermic reaction, so it's producing heat as the nitrogen and hydrogen are reacting together. And just on its own, the ammonia plants would produce 75–80% of the steam, of the energy required to generate the steam for the solid oxide. And if you're making fertilizer, so you're adding a nitric acid system on it as well, that's exothermic, and you get to all the energy you need to produce it. And if you're doing a greenfield design, well, then you're actually removing capital cost from that ammonia plant, because now you haven't got a big power generator. They normally have a big turbo generator to recover that heat. So you generate steam with a big steam generator anyway, and then they put it through a turbo generator and recover a couple of megawatts of electricity out of it. Well, actually, I don't need to do that. It's more efficient to take that energy and stick it straight into a solid oxide to make my hydrogen, rather than taking that electricity and putting it to an alkaline plant. So it's another really key aspect. You can't just think about the electrolyzer cost. You need to think about, well, actually, what is my full greenfield plant cost, or my integration with my full plant cost with that industrial facility? There's additional savings you can get there with the solid oxide. You're on mute, Chris, I think.
I am on mute. There was always going to be one of those. But John, you mentioned that the lower temperature aspects of the solid oxide technology from Ceres, and maybe I just wondered if there was a run-on for when you come to the plant design, what type of metals or materials need to be used if you're running maybe a higher temperature version of solid oxide operating at those 750s to 900 Celsius range you spoke to. Does that change the cost? Does that change the balance of plant needs, which obviously Gareth spoke to how important balance of plant is in the total cost?
Yeah, absolutely. Yeah, we do see a bit of a differentiator there with our operating temperature range. They tend to fall in sort of industrially recognized temperature ranges for materials, for example, but also, you know, the thermal expansion and also the heat loss is a really important consideration. So with higher temperature solid oxide technologies, you know, you're going to be into quite exotic materials, quite high cost materials, and then you want to closely couple the heat exchangers to the stacks. So that tends to lead to an architecture where it's very distributed. You've got lots and lots of heat exchangers, all closely coupled with quite expensive materials. Ceres' operating temperature means that actually you can have one big heat exchanger pack, which is serving lots of those stack array modules. You can have reasonably long pipe runs between those things. You know, they can be insulated easily. The thermal expansion isn't too bad. And if you do all that, you know, lower cost materials, much bigger heat exchangers, fairly standard design practices, then of course the capex costs reduce quite significantly in that regard.
Yeah, I think one of the key bits was the strength of the steels that we're able to use. So we're able to go down to the 300 series type stainless steels, because as you go towards the 650 temperature range and going into where some of the higher temperature SOECs run, your strength of the material really drops off a cliff. It's not linear. It goes boom, falls away. So you're trying to keep it in that range allows us to use those cheaper steels for a good part of the design. It's really helpful.
And whilst we're on technology comparison, it may be pretty useful to speak about the views potentially from Gareth here about the different technologies at play, you know, PEM, alkaline, solid oxide, and the landscape of these different technologies. Where do you think solid oxide compares at the moment? Obviously, it's still nascent and it's being developed, but how do you view the landscape at the moment, Gareth, on the different projects you're helping with?
Yeah, so we see this. We always put SOEC into our analysis, although most of our clients ask us to do that as well. There's definitely a growing interest across the developers in solid oxide. They can see the benefits of it. And whenever we do it, we're nearly always coming up with, in fact, every single time we're coming up with 10% or greater reductions in the LCOH, typically even more than that. And that really means that the developer interest is really huge in this area for especially people that are developing ammonia plants, which is where a lot, when the majority of hydrogen goes to now, if you ignore oil refineries. So they're really looking for that. And one of the key pieces that they ask for, and one of the reasons why they tend to go, oh, actually, I want to go with alkaline, is technology maturity. And if you look at alkaline, a couple of 100 megawatt scale facilities have been built in the past. So people know this technology. Now, the issue with that is that those alkaline electrolyzers in the past were run flat out off hydro. They weren't varying up and down. And one of the newer ones that's been built in China, I think it was for Sinopec or something like that. That was, I think it's over 100 megawatt as well. They had some issues with that. They had, when they were trying to vary it up and down, they had gas crossover and those sort of things. So as every new technology we bring into the market, you come across new things, especially when you change the use case. And I think the key thing about Ceres' technology is that they've already got a lot of it demonstrated already with their fuel cell side. So it's actually a lot further along than some developers think. They think, oh, this is completely new coming out of the lab. It's not. It's in the market now, but as a fuel cell, all we're doing here is changing it over to work in the electrolyzer form. So it's that convincing people and having that credible path to demonstration, which is what Ceres is developing and doing. Getting this into the market is really key so that developers feel comfortable, and especially people financing these projects, right? It's the finance people that are driving a lot of these technology decisions. They're going, I would say I've got non-recourse finance. I don't want to take that risk. I would much rather you go with that alkaline system, even though it might mean that the project's 10 or 20% better off from a cost perspective, from an operating cost perspective. It doesn't mean that I want to take that risk. So it's trying to get the market ready to take some of those risks. And the market is getting there now, I think. There's some bigger and bigger solid oxide deployments going out there, and as from other companies, and Ceres has got their 1 megawatt one, and when we get to the next bigger one, in the multi-megawatt scale, it will really demonstrate to the market that once you've got that core building block demonstrated, you can just repeat it then, and then you've just got a little bit of risk, but that risk is on plant that you well know. It's the same kind of plant you have in an oil and gas facility, so the risk is much lower when you go to the balance of plant. So it's just getting to that demonstration of that core piece.
And John, was there anything you wanted to add on the solid oxide market at the moment and competitors that you're seeing?
Yeah, well, I think I'll just come back to our business model again, because I think it provides for further levels in the supply chain than even fuel cells do, right? So in the fuel cell market, we would license to maybe a cell and stack manufacturer, but they tend to also be the system and the product company as well. And you look at examples of our current partners, so they'll be making the components but also designing them into systems and then selling the systems on the market. Whereas in SOEC, you're going to have cell and stack factories, and obviously that's high volume ceramics manufacture, making many cells a year. Then you've got the kind of industrial process equipment manufacturers. So you've got, you saw on the video, the stack array modules. They're quite large, right? So they're going to be built in factories, but they're sort of akin to very large engine sort of scale, and the electrolyzer module itself. And then, of course, you've got companies who are then going to be the overall project engineering companies, such as Atkins and other EPC companies, who are then going to be working out the best way of deploying all that technology and the rest of the plant to provide the best solution to the client, whatever their application is, whether it's hydrogen for steel or ammonia or synthetic fuels or whatever. But so I think that our business model provides a really rich business opportunity across those different areas, and then that's what we're seeing at the moment, is really strong interest right across that value chain of companies who are interested in moving into that space with a proven technology in fuel cell. We've been working on it over 20 years in fuel cell mode. We're effectively operating it in reverse, but a lot of the the atmospheres, the temperature, the material selection that it's working in are the same pretty much. So really, we're in a phase of now maturing and optimizing, but it's not new invention. It's not starting from scratch. It's a very mature technology basis, which we're just moving into a new application area.
There we go. Sorry, the unmute wasn't working for me. And Gareth, I mean, when we're speaking about de-risking these projects and getting first investment, large-scale investment decisions into solid oxide, I wonder if you can maybe elaborate on the potential balance of plant savings and the big areas or the big building blocks of where you would see the save come for the project developer. So maybe on the renewables that might be needed, the lower levels of installed wind and solar, potentially talking about the substation, which would be the point you made earlier. Just to really ram that point home would be quite helpful. Thanks.
Yeah, I think so. I think we made the like you alluded to, we made the points on the saving electricity consumption and the saving in electricity consumption across the life of the system as well. So hammer that bit home. And if you think about it, one of the biggest costs, if you're doing completely greenfield, and one of the things is a lot of these projects require the renewables to be built. Okay, those renewable costs are the same as the big industrial plant. They cost a lot to build the renewables. So saving 30% on your renewables, actually your overall project cost goes down massively by having that efficiency versus alkaline, the current alkaline and PEM. One of the other key bits is the construction cost. The construction cost is actually really high. Don't just look at the module cost. The electrolyzer module cost typically is 1.8 to 2 times that to get you to what a facility cost is. And that facility cost, is a big chunk of that is actually the construction phase. So being able to minimize that by making the plant modular really helps. Now, the way LNG facilities, and this is a kind of an analogous piece where LNG's got to a stage where it's cookie cutter plant design, where they have these huge modules, 30 meters by maybe 100 meters in terms of area and weighing tens of thousands of tons, and they're just picking them up, building them and dropping them onto site. Now, what we've looked at with Ceres is, right, okay, what is our mass repeatable unit that I need to get? And then I need to make that very transportable. And then what you can do is you can build up these huge modules if you wanted to drop them on site. So it's changing that change in thought process about the whole design of the electrolyzer really helps drive down that cost and make it more applicable to the developer. So that's some of the bits that we came to now.
Maybe a good time to open up to some of the Q&A that's come through on the line, or through the platform, and first, moving to the recent contract that you announced, or Ceres announced with Shell to design that 10 megawatt pressurized module, and can you just give some more color on the work that's what will go on for Ceres here? What exactly will Shell be paying for, and what else might you be contributing to that contract? Any color there?
Yeah, of course. So as you're aware, we're testing our first of a kind technology demonstrator at Shell site in Bangalore. And as a next step, effectively, we're leveraging the work that we've done with Gareth and the team, taking that starting point as a reference design, but then transferring that to Shell to get their input on that. Now they're looking at particular use cases and end uses of the equipment. They're also looking to bring their own differentiation to their projects as well, and that's really how we work at Ceres. We'll take a reference design, a starting point that we've done a fair bit of work on, a fair bit of thinking around, but work with our partners to see how they can bring differentiation to the design. Maybe they'll have some suggestions about how best to design the stack array module or the electrolyzer module, how many of those are required, or what the overall plant design is going to look like. So it's a first step in that direction. It's a 6-month design study to get to a point where they may well then take a further decision to move forward with Ceres into something a bit bigger and a bit more tangible.
Okay, super clear. Thank you. And another question on the module size. So building in units of 8.6 megawatts in size that will scale up to give the 100 megawatt offering. And I know, Gareth, you did mention during your remarks that maybe there is a limitation on size for how big the stacks can go in solid oxide. I just wondered if, and there's a question that's come in, will you build in 10 megawatt modules, or will you keep at these 8.6? Will that 8.6 gravitate up towards 10? How are you guys thinking about the system and the modular design?
I did the unmute thing then. There is definitely you're able to go bigger than 8.6, right? There is an ability to increase the size of that module. I mean, at the moment there's sort of 12 SAMs in that module, and there's an ability to add more to that. There will come a limitation at the point where the pipework gets so big that you then have to start using things like expansion bellows and things like that. And we've managed to avoid that so far. And that's kind of where we got to with the size of that. Now, if you increase the size of the stack inside by, say, going from 30 to maybe 40, 50 kilowatts within the same vessel, you're jumping well into the 10 megawatts, 12 megawatt size with those 12 SAMs. So there's a bit of a constraint in terms of the pipe expansion, those type of things, but there are ways that you can increase that module size even further. I think John might want to talk about that, but there's a piece around the stack really helps that.
Yeah, absolutely. So there's flexibility there. We purposely kept the electrolyzer module, rectangular. If you wanted to add some more stack array modules on for whatever reason, then you could. There's also a question around redundancy and maintenance and taking modules down for maintenance on an overall plant level. So we were looking, for the particular study that we showed the video around, we were looking at 100 megawatts, so 12 electrolyzer modules, and thinking about, if you had to take one down for maintenance, what would you be okay with in terms of a reduced capacity for a period of time? And that was a bit of a consideration in that overall concept. But there's no real limitations. I think, again, with the stack, what we're trying to do is keep the stack platform common at the moment. So licensees with factories who are making SOFC stacks could use the same factory to make SOEC and the cell footprints. There's a lot to be said for commonality in that approach. And that's really why we ended up at the stack array module, because SOEC stacks tend to be, just by their nature, smaller than alkaline stacks, right? Alkaline stacks are enormous, right? But we were packaging stacks into the pressure vessel there, and then for the Ride design study, that's 720 kilowatts, in a pressure vessel, and basically that's like a super stack, right? So it looks exactly like a stack to a process designer, and it doesn't really matter what's going on inside it, to be honest. It does exactly the same thing. It's just got higher power input, higher hydrogen output.
Yeah, I think one thing to note on that when people think about it is that 720 is quite a little bit closer to a megawatt when you compare it to alkaline in terms of production capacity. So you'd have to put a megawatt size stack in there. So the 8.6 megawatt of electrolyzer capacity that we've got there is equivalent to a much bigger alkaline plant in terms of its production rate, easily over 10 megawatt. So just to keep that in your minds when you're thinking about it, don't always think about the megawatts. The megawatts are meaningless in terms of production. The production kilograms an hour is what's key, because that's what you're really trying to put into your facility. So just thinking about that when investors are looking at it, it's not one for one when you're comparing alkaline and PEM. You've got to look at the efficiency.
And alongside that, is there any comment you can make maybe on the sort of the current density? I mean, equally playing into the footprint, being that much smaller. I mean, compared to alkaline or your most basic sort of atmospheric alkaline, I would consider that the solid oxide has a higher current density in terms of maybe amps per centimeter squared or amps per meter squared against the alkaline guys. But I don't know if you have previously given that analysis. I just wonder if that is the case.
Well, so you can get into a bit of an academic conversation around cell current densities, and it's all quite interesting. In fact, I mean, the Ceres, because we operate at a lower temperature than high temperature SOEC, we have a lower cell current density, but then our cells might be a bit closer together in the stack. And to be honest, by the time you've designed them into the array modules and the electrolyzer modules, that cell current density gets massively diluted into the sort of footprint of deployable equipment that we were looking at earlier. And it doesn't really, by the time you've got to that scale, you don't really care about your cell current density. What you care about is your CapEx, your OpEx, of course, and your land use. And some of the stuff, I mean, Gareth, you did a bit of looking into this, really comparing, we talked about that 120 square meters for the electrolyzer module in terms of how much hydrogen are you producing per square meter of land, right? And I think we're coming out pretty favorable in terms of our production density, I think, Gareth.
Yeah, I think we were comparable or better than alkaline from memory. I think PEM intrinsically is a little bit higher density, but I think we were 1 million miles away from some PEM manufacturers, depending on which ones you looked at. And it all comes down to how they do their balance of plant as well. So, if you looked at a smaller scale, they're quite comparable. But as you scale up, if that company hasn't done the vertical scaling of their balancing plant, then their footprint explodes as well. It doesn't stay the same. You get a much more linear increase in that, which actually you can take that off quite a bit by doing the design methods that we've used.
And on a follow-up question was coming in on the pressurization of the stacks. Will you also continue to develop, atmospheric non-pressurized SOEC modules, or will everything in the future probably be designed to be pressurized at that sort of 2-bar stack level to then go to 30 bar?
Well, look, I mean, that's the direction of travel that we're looking at the moment. But again, we're a licensing company, right? So if a company wants to make atmospheric SOEC, then they're absolutely welcome to do that, and we would sell them a license to do that. That's absolutely no problem at all. It's just, for our studies, we see in terms of industrial applications, industrial integration, we see a real advantage of being able to have a reference design of the technology which can operate in a pressurized manner, but it doesn't have to.
That makes sense. And Gareth, I mean, I wonder for the hydrogen hubs, if nuclear has been involved in your hub, and if it has, I mean, nuclear obviously would have some key. I mean, clearly waste heat is present quite a lot. Some key attributes to be associated with, if you were to build a plant really close, that would make a lot of sense. So, have you seen a lot of studies that are starting to take place on nuclear, or is it still very early for nuclear and solid oxide to be paired together?
Oh, I've seen a couple of studies now. We've done some studies ourselves, and we're also actually doing a study at the moment, a little bit based on Ceres' technology, actually, for integrating with our own nuclear power plant design. So yes, like you said, you have steam available and you have electricity available. So both of those things are the key inputs. In terms of in the hub, no, I think there's only one nuclear power plant in that part of the US, mainly because there's huge amounts of hydro. So the Pacific Northwest has that, but other plants in the US, what a lot of people don't realize is that nuclear power plants, actually most large thermal generating plants, actually use hydrogen on site to actually cool the generator units and to cool the stator. And some of the plants in the US are actually importing liquid hydrogen in large trailers 2 or 3 times a week just to cool the bait of the power plant with hydrogen. So nuclear power plants are well afraid with using hydrogen on site. So there's no general issue with integrating this with it like you would any other industrial facility. And it's a good partner because it can run all the time. Basically, they run with 95 to 97% capacity factors on nuclear. So yeah, I think nuclear is a good use case. I think if you get to the right one, to the right power price. So a lot of the fully depreciated plants in the US, they're at very low constant power prices. They would be great to integrate with to develop hydrogen for industry, I think.
And Gareth, I'm just thinking now about obviously we've spoken about the different technology classes, we've spoken about the scale up and the opportunity for solid oxide, but what have been the main sort of challenges on the engineering side with solid oxide as a technology class? Are there still hurdles that need to be jumped over? A question here, just asking, what are the negatives? Give me the downside, right? What could potentially be the weaknesses for the technology? We know the weaknesses for alkaline is potentially a lack of flexibility, also very big unit sizes, hard to move around, potentially hard to service. We know that PEM can be expensive, iridium is present, and maybe serviceability might also be a challenge, and recoverability of the iridium. What kind of stuff should we be thinking about on the electrolyzer side that you think could be a challenge for solid oxide?
I think one of the challenges for solid oxide is the life at which the stack lasts for. And some of the stuff we've been working with Ceres on is really helping, and we hope to extend that out, I think, quite significantly. And that adds a costing because you're probably changing it out maybe once or twice extra in the life of the plant versus an alkaline or PEM stack. But that's why you weigh, when you're doing the overall analysis, you still end up with 10 to 20% lower cost hydrogen, even when you account for those change outs. So John, I don't know if you want to comment on the stack life and those type of things, maybe?
Yeah, I think you're right. So certainly solid oxide is in terms of a technology class, it's been seen as quite expensive from a capex point of view because of the materials issues and those sort of things, and robustness, not just in terms of just general durability, but also in terms of cycling. People say, oh, you can't thermally cycle it, it can't load follow, etc., etc. Now, not all those things are true actually. So we can certainly load follow, but ramping up, so the example that is normally used is like, you've got a wind farm and you're using curtailed wind and you want it to ramp up when the wind blows and then shut down, and how are you going to ramp the temperature up and down in time? And that's sometimes one of the questions, right? But actually for solid oxide, I think you would keep it at temperature, so you warm it up and you leave it at hot idle, we call it, and it's just ticking over, and then when power's available, it operates, and then it ramps down again. But the point being really that Gareth alluded to the point earlier that actually if you've got an electrolyzer asset you spent many millions of dollars or euros on, you want to be sweating that asset massively, and that's really where you'd use it for an industrial application. You're really getting the most out of it in that regard. Now, of course, I suppose we at Ceres are trying to address some of those issues in terms of our technology. So trying to approach the capex cost by the lower temperature point, and also the robustness too. So it's not a purely ceramic high cost stack, which is quite sensitive to thermal shocks. We've got a steel architecture which is actually quite robust to plant trips and shutdowns and emergency stops and those sort of things. So that's kind of what the angle that we're trying to take, is that actually we're trying to address some of those downsides of solid oxide through our particular technology basis.
Yeah, and I suppose I'd also add from an industry point of view, PEM has been developing, so stack life has improved for PEM. You're still probably on that journey in terms of stack life for solid oxide, and you guys are at that lower temperature level. So would that potentially help as well on stack life, or is it pretty similar across the different competitors that you all see in the market?
It does, and also the other point I'll make, it's plant life really you're worried about, not stack life. So clearly stack life is important, but if you carry out some fairly good approaches in terms of your overall plant, making sure that the steam coming in is of a certain quality, really trying to reduce the ways poisons can get into the stack. I mean, something we're looking at is actually, do you need airflow? Do you need airflow at all? Because that's definitely the way that poisons can be introduced into stacks. So thoughtful plant and system design can really improve anything. A bit like a car, really. You wouldn't run a car without a fuel filter or an air filter. And it's the same with stacks. You've got to select materials correctly, get the right filtration in place, get the right operating strategies, and then you can actually see some really significant overall plant lives.
Just coming up on the hour, so last question to wrap it up. Question coming in on the largest electrolyzer stacks for solid oxide out there at the moment. So there's a 4 megawatt system, maybe from Bloom Energy. When do you believe Ceres could be in place to deploy their first 10 megawatt unit with a partner, or 20 megawatt system? When do you think that would be feasible if a partner came knocking on the door today to ask?
Right. Well, great question. And I think that's really what we've been working towards, so the work that we've been doing with Gareth, we've got that reference design available now. So that 8.6 megawatt, design is now ready to go into detailed design. We've got stack manufacturing at that capacity available. And we're just going to start building the first prototype stack array module this year. So next steps are exactly that, finding a commercial pilot project where we can site that 10 megawatt scale commercial pilot. Lots of conversations going on at the moment. Haven't got a definitive answer to that question just yet, but that's definitely our next step.
Brilliant. Well, a great place to end. Thank you both, Gareth and John, for your time today, and for the audience participation for the very insightful questions. And I'll now pass it back to Paul.
That's great. Chris, Gareth, John, Elizabeth, thank you once again for updating attendees this afternoon. Ladies and gentlemen, could I please ask you not to close this session, as we'll now automatically redirect you for the opportunity to provide your feedback in order that the company can really better understand your views and expectations. It's only take a few moments to complete, but I'm sure it'll be greatly valued by the company. On behalf of Ceres Power Holdings PLC, we'd like to thank you very much for your time this afternoon. Good afternoon to you all.